AP Calculus AB, day 6. Or sorry, Unit 6, day 1. Let's see. Related rates. So we did a little introduction video. So now we're going to try some. We're going to bring some calculus into this and start to kind of wrap our heads around this. So we'll start easy. Vonderheide is increasing the volume of spherical balloon by 2 cubic inches per second. And how fast is the radius changing when the volume is 36 pi cubic inches? So this is very similar to what I demonstrated. I mean, we could draw a picture. Sometimes it's helpful to draw a picture. I mean, this is a sphere. It looks like a circle, and then you can kind of draw like that. Nice. Looks like a sphere. Anyways, what formula relates to the volume of the radius? So we have increasing volume. This is dv dt. This is the derivative of the volume, and it's positive because it's increasing. You got to watch out because if it says decreasing, it's not going to have a negative, and you need to put a negative. How fast is the radius changing? So we're looking for dr dt. How fast is the radius changing? The rate of change of the radius. It's a derivative, dr dt. And then they're just telling you straight out when they want you to, something else that is true when at the moment that you're looking for this. So we're going to probably have to use that somehow to get some information. So let's not worry about the derivatives yet, other than we have this derivative and we want this derivative. So how can we relate the v and the r together without derivatives first? What formula relates the volume and the radius? And sometimes it's pretty obvious. It's the volume of the sphere, 4/3 pi r cubed. So we got some geometry formulas to remember from geometry. And so now what we're going to do is we want to get the derivative of the volume in there, and we want the derivative of the radius. So we're going to do dv dt. And so the pi is just a number, so it's r cubed. So we're going to multiply by 3, power rule. I'm going to get 4 pi r squared. Now, you should know something's wrong because we need dr dt, and you don't have a dr dt. So you got to follow it up with dr dt because this is implicit differentiation. Okay, so first you get the formula, and then you take the derivative implicitly. And because we're taking the derivative with respect to time, we first took the derivative with respect to r, the outer function. And now we got to say, well, r is the function of time, so we need to follow up with the derivative of r with respect to time. So you got to make sure that you don't forget that. But it's going to be hard to ignore it because that's the thing you're looking for. So now we have this, right? We have that. That's a positive 2. We don't have the radius, and this is what we want, dr dt, right? This is what we want. This is what we have. If what you have doesn't come up and what you want doesn't come up, you probably miss something. So the thing we got to figure out is what the radius is. And so that's where the volume comes in. So the volume equals 4/3 pi r cubed, just regular old volume, and we know that the volume is 36 pi, right? So we're going to use that to figure out what the radius is supposed to be. So we're going to divide both sides by pi, which cleans up nice. We're going to multiply both sides by 3/4. And so then we get r cubed equals 27. And then we're going to take the cube root of both sides. No plus or minus is an odd root. So the radius is 3. So that's what goes in here, 3. So we had to find r, need r. So usually there's going to be some other given information that's true about the moment, and you're trying to find something else, and you need to get something from it. So now we can simplify this and solve for dr dt. So d r dt equals 1 over 18 pi. We need to put the units. So what are the units of r? Well, the volume was cubic inches. This is one-dimensional units. That should be inches. And the time was seconds. So the unit should be in there. And this is it. So you got to make sure that you do the units. Otherwise, you're going to be losing points over and over and over again. Okay? Make sure you put the right units. It's not cubic inches. It's not volume. Okay? Now, the other thing to consider is we got a positive answer. Does that make sense? Is the radius increasing as the balloon is, the volume is increased? Yes. So you always want to ask yourself what the sign of your answer should be. Okay, let's try another one. So oil spilled from a tank creates a circular pond whose area is increasing 100 square inches per minute. So it's flat, spreading on the surface. How fast is the radius of the circle increasing when the pond has an area of 25 pi square inches? So let's look through here. It creates a circular pond whose area is increasing. So this is dAdt. So I like to do this, write down this stuff. dAdt, it's increasing, so it's positive 100 square inches per minute. Okay. How fast is the radius increasing? So we're looking for dRdt. So I like to make a note of that. When the pond has an area of 25 pi square inches, so we're probably going to use that to find some dimensions that we need to plug in our formula. So first thing, we can draw a picture. It's a circle, and it's increasing in size. It's getting bigger and bigger and bigger. Okay. So we expect the radius to be getting bigger as the area increases, but we need a formula to connect the area with the radius, the rate that we know and the rate we want. Area of a circle is pi r squared. So there's a lot of geometry in these problems just to start it off. Then we're going to take the derivative with respect to t implicitly. So derivative a, that's the same thing as like a prime, 2 pi r, but then don't forget the dRdt. Got to take the derivative implicitly. This is what we want, right? This is what we have. So positive 100. Now, I always put this plus or minus sign in front because it's so easy to mess it up because it depends on the wording. And we should get a positive answer when we're done. Now, the one thing we don't have is the radius. So that comes from the fact that they told you that the area of the circle, pi r squared, is 25 pi at this instance. So we're going to solve for r. Square root of both sides, plus or minus, but we're just going to use the positive one because no such thing as a negative radius in these problems. So we're going to plug the 5 in, and now we can solve for dRdt. So I'm going to divide by 10 pi, and so dRdt equals 10 over pi. The units are going to be radius. It's got to be one-dimensional inches over time, which is minutes on this problem. And it came out positive, which it should. So there we go. That's how you do these. So let's try another one. Now this one, we'll make it a little more challenging in a couple different ways. At night, a woman 6 feet tall walks at a rate of 4 feet per second towards a street lamp 30 feet above the ground. What is the rate of change of the length of her shadow when she is 8 feet from the base of the light? What is the rate of change of the tip of her shadow? So we got to get a picture going and thinking. So we have a street lamp, right? Street light, and this lady's walking towards the street light, and it casts. This might remind you of the tree on the hill problems from a while ago. Cast, the raise the light, cast the shadow. Right? I think it's good to have a simple picture. And she's 6 feet tall, right? And the street lamp, I think, is 30 feet tall. It's not changing. So label that, and it says when she's 8 feet away from the street lamp. Okay. So what is the rate of change of the length of her shadow? Okay. Well, let's see. The rate of change of the length of her shadow. So we need I think we need a variable for the length of her shadow to get its derivative. So I'm going to just call it x. All right. Now they gave us a rate, right? It says she's walking at a rate of 4 feet per second towards the street lamp. So we could draw a little arrow. A lot of times on these problems, I like to show movement with an arrow. So she's walking at 4 feet per second. Now, here's the challenge. We want to know dx dt, right? But what is that rate? We need a variable for it, and we need to tie it to the picture. So it's not as clear this time as last ones. But that's how fast she's moving. But I don't know if you guys agree that the length between her and the lamp is changing by that same rate. So that's where we're going to put another variable. I'm going to call it y. So this is actually dy dt. Now, is it positive or negative? Is y getting smaller or bigger? Longer or shorter? It's getting shorter, right? So we got to tie a negative to this. Her rate that she's walking isn't considered negative 4 feet per second. She's walking to the right. You might consider that positive. But now that I've tied it to this variable in the picture, which I needed to do, it is now considered negative relative to that variable. Now, how do we relate dx dt and dy dt? How do we relate x and y? Well, I see a lot of I see a couple triangles. I see a big right triangle and then a smaller right triangle here. And these are similar triangles. And that's what we're going to use here. And that comes up on a fair amount of problems, similar triangles. Again, some geometry stuff. Similar triangles are proportional, okay? Similar, that's the similes for similar. They're not congruent, but their sides that match up have the same ratio. So like there's lots of different ways you do it. You could say this over this, 6 over x would have to equal this over the corresponding side over here, which wouldn't just be y, it'd be x plus y, right? I mean, so there's a lot of ways you could set this up. You could say 6 over 30. You could do one side over the corresponding side. It would be x over x plus y. But in the end, these are all giving you the same relationship. I personally would cross multiply. 6x plus 6y equals 30x. And we could even solve for y. Subtract 6x from both sides. 6y equals 24x. I mean, we could even take it all the way down to getting y by itself, which, I don't know if that's super helpful, but we could, there you go. That's the relationship between x and y. So now we're going to take the derivative. We haven't done any calculus yet. It's all geometry so far and algebra. Now we're going to bring in calculus. Derivative implicitly with respect to time. dy dt equals 4 dx dt. 4 is just a number. Don't need to do product rule. We're always thinking derivative with respect to time on these time rate problems. This is what we want. No, that's what we have. So we have this, right? This is what we want. So we're going to plug in -4. Now, by the way, do we think that her shadow is decreasing or increasing? Is her shadow getting shorter as she gets closer to the street lamp or longer? Think about it. Think about real life. What happens when you get close to the light source? The shadow gets shorter. Okay? So it should be negative. And that's another good check. That if you forgot to put the negative on that dy dt, it should hopefully jump out at you. So dx dt equals -1. The units are x is feet, and the time units are seconds. So -1 foot per second. So it's getting shorter. Okay, so that was definitely a little challenging. Now the second part says, what is the rate change at the tip of her shadow? So the rate change at the tip of her shadow is saying, well, how fast is the tip of the shadow moving? Okay, that's not dx dt. dx dt is just how short her shadow is, how quick this is changing. I'm going to draw another picture here. Now, by the way, the 8 didn't even matter. We never had to put y equals in here after we did the derivative. So it's actually, her shadow is changing at -1 foot per second, no matter how far she is from the street lamp. And you definitely don't put that 8 in before you take derivatives because y is changing. So in this case, we're trying to figure out how fast this is. That's kind of like how fast she is. So you need the distance between her and the street lamp. So I'm going to create a new variable z. I'm going to say, you know what? We're looking for dz dt. And so how does z relate to x and y? So z equals x plus y. And so then if we do the derivative, dz dt equals dx dt plus dy dt. And then we would use our answer and given information before. So dx dt is what we just found, -1, and dy dt was -4. So dz dt equals -5 feet per second. Now, I don't think we should put the negative in this answer. If related to z, yeah, z is decreasing. But if we're talking about how fast her shadow is moving, I would be more likely to say 5 feet per second and then indicate the direction toward the street lamp. Now, the interesting thing is that the speed of the tip of her shadow is moving as fast as she is, plus how fast her shadow is changing. And by the way, the speed of the foot of her shadow is still going to be -4 feet per second. So it's like the head is catching up with the feet the whole time, right? So it's got to be moving faster. And again, it didn't matter if she was 8 feet away from the lamp or more or less and didn't even come to the calculation. So that was definitely a tougher one, involves somewhat triangles, some other geometric ideas. Now the one on the back, I'm going to save for a future day, okay? So you don't need to do, we're not going to do the one on the back right now, but we will in the future, so don't throw it away. Your assignment is right here out of the textbook, and most of them are odd, so check them in the back of your book. You need to be drawing pictures on most of these. You need to be showing your work. Make sure you have the units on these answers. I will actually not give you credit on homework if you don't put the units. But try these out. We're gonna spend a lot of time on these. These are definitely challenging when they're new, and this will be like a good chunk of your final. This is our last unit of the first semester. So try these problems, and then we'll go from there. We're gonna spend quite a few more days doing problems like this to get good at them. Yeah.